It's my very special pleasure to introduce Professor Timothy Gay from the University of Nebraska, Lincoln, to talk about the physics of football. And it's a fairly timely talk because we had the Super Bowl yesterday. And I known Tim for a very long time, and I know he got his undergraduate degree at Caltech and went to graduate school at Chicago. And then he was here at Yale for 4 years or so, working with Vernon Hughes. Then he went to Missouri School of Mines. I didn't know about that before. And he was there for 10 years and was tenured, and then moved to Lincoln, Nebraska in the early 90s. And he's been there ever since. And he wrote the book, The Physics of Football. It was first version, I have the first edition, was called Football Physics back then. And it follows a long tradition of Yale faculty members writing a sports book. Robert Adair wrote The Physics of Baseball. And people say he wrote the book on the subject, and well, he really did. So, yeah, and so it's particularly interesting because, of course, football was invented, or at least put in its final form at Yale by Walter Camp and company in the turn of the last century. And about a year ago, I was contacted by WGBH Nova to talk about some physics of football, and they were looking for something interesting. And I sort of mentioned this thing about the spiral pass, and that nobody understood it. And so I started looking at that a little bit, and I think they found Tim on their own. And he had worked out the whole theory. It's really very, very complicated. Well, I won't say very complicated, but all the details are as usual when you have a hydrodynamic problem. And he has a good explanation of it. And he'll tell us about that today, I believe, in addition to a lot of other physics associated with football. Without further ado, I'll
Can you all hear me? In the back? Good. So, Steve, thank you so much for inviting me. I
think it's pointing the wrong way.
Oh, it is. All right. There we go. Thank you. Now it should be better. No, I've got it covered. Here, let's do this. No, that's going to make it worse. I think that's as good as we're going to do. I was really pleased when Steve called me up and invited me to come. When I was here between 1980 and 83, I had many good physics learning experiences in physics club. Back then it was done on Friday at 4 p.m. in the other room across the way. But I learned a lot and got to see how physics was done in the big leagues, I guess it would be one way of putting it. So what I want to tell you about today are some physics points that are of interest, most generally to a lay audience in the stands at football games, but on rare occasion to physicists as well. This all got started when a guy named Jeff Schmall, who was the head of Husker Vision, which was the audio-visual arm of the athletic department at Nebraska, decided it would be good to have some sort of science put up on the big jumbotrons. We were the first university to have big jumbotrons in our stadium. And usually they had things like, cute photogenic kids asking football stars what their favorite color was. And he thought, no, we're an academic institution. Let's try to get science involved. And that sounds like physics in the case of football. So he sent a producer over to the physics department, and she walked into the front office and said, I'm looking for a physics professor who loves football and just loves to hear himself talk. And they all stood up in unison and said, well, that would be Tim Gay. So she came down and pitched this to me and immediately got me hooked. I have a long history with the game of football, and indeed I played football in college. Let's see if I can get, I think maybe I need to do this to advance it. This is on. I'm trying to get it to advance. It's refusing to advance. Why is that? Can I do? Yeah, okay, let's try that. Boy, now there we go. Good. I played on Caltech's team, which was so notoriously bad that the Wall Street Journal featured us in their joke column back in 1974. And I've really tried to suppress the memories as well as I could, but a couple really sort of stick out. One about our quarterback, Greg Hoyt, who was, I think, about 140 pounds and was, 5'3". As throwing a pass and it comes down the field like a sack of wet laundry. The other thing that rang true was at football factories like Ohio State, tens of thousands of dollars were spent in recruiting high school superstars, and networks of hundreds of alumni helped ferret out and woo likely prospects. At Caltech, recruiting consists of Coach Gutman lurking in the bushes while students play intramural touch football and jumping out periodically to try to persuade promising youngsters to sign up. Most don't. A good season for us would have been like 7-2, and we would lose to Laverne Bible College and Whittier College. One time we did play the University of California, but it was the Riverside campus, and it was the freshman team, and we lost 47-0, I think, as I remember. So this was all very exciting for me, except I did have a concern, and that is this. I was worried. Let's see. We'll try to get. Yeah, I was worried that if I got into this, I might be taken less seriously as a scientist. So here we have. This is during the Carl Sagan era. And it sort of reminds me of Alan Bromley and Vernon Hughes in one meeting I attended. One thing I'll say for us, Meyer, we never stooped to popularizing science. And I was, again, worried that might lower my reputation in the community. I have to say that instinct was wrong. My colleagues have been very, very supportive. And I think it's really seriously important to explain to the public, who are, after all, paying the bills, why what we do is interesting and important. And of course, the best way to do that is to connect with something your audience is interested in. And of course, in Nebraska, they're interested in football. So we did a couple of pieces, and I learned an important lesson, and that is that you really have about a minute to get across an idea, because after a minute, people are starting to look around elsewhere, and you lose them. So it was tough to get a kernel of a physics idea across in that short amount of time, but it worked okay, as you'll see. So now, if I try, there we go. So this had been going on. I did these lessons for about a season and a half, and it got some national attention, which I'll now share with you.
Finding about this evening, science in the state. For some years here, we had a colleague from Nebraska. She was passionate about the news and the University of Nebraska football team, the Cornhuskers. Our colleague had a sense of humor about farm jokes, but she never told us about the physics. For that, ABC's Bob Davison had to go all the way from here to Lincoln, Nebraska.
There's almost nothing Professor Timothy Gay likes more than teaching physics.
We experience time in a completely different way than we experience space.
Nothing, that is, except the University of Nebraska football. In football, Professor Gay sees not only the game, but his beloved physics in action. Maths, philosophy, on display in real life. Professor Gay decided football was a perfect way to make physics understandable and fun. So now, how can we reach a wider audience? With television, of course, a really good television.
Football physics with UNL physics professor, Dr. Tim Gay.
The giant screen at Nebraska's Memorial Stadium now shows Professor Ye's physics lectures. The class size, 77,000. This game, the subject was energy.
Both teams combined expend enough energy to lift the pickup 10 yards in the air, enough for a vertical first down.
Other video lectures have addressed momentum at force.
Proves momentum roughly 1,000 kilogram meters per second, and 3 times that of the Oklahoma player effectively stops the run.
And gyroscopic motion.
Right? A football must be spinning for it to be stable in flight. I wanted to talk to as many people as possible about physics. I was worried that the fans would say, I'm here to see football. We don't really want to go back to school and learn about physics.
The professor needn't have worried. Fans pay attention. And so do the players, including 320-pound offensive tackle Adam Joel.
Not like most things where they show something and not everybody watches it. Everybody's focused on watching it, and it's very entertaining for the people.
By season 10, fans may no longer talk about a good punt, but about the angle at which it was kicked. And how the moved on the proper axis. And if all of this makes the Cornhuskers better, colleges soon will not only have a team physician, but a backup football team physicist. It was an ABC News, nothing but rights.
So there's actually a fun, well, there's a couple of points from that to take away from that video. The first is I'm not going to be getting an equity card anytime soon. The other interesting thing was that the football player, Adam Julch, that they interviewed was actually in my calculus-based introductory physics class, and he got the highest grade in a class of 300 people. So not all linemen are dumb. Most are, but not all. Okay, so the first idea is that when we watch a game of football, what we're really seeing, of course, is classical physics in action, specifically Newton's 3 laws. So, and this is a bit like carrying coals to Newcastle, but let's review the 3 laws for a second. So the first law is that mass wants to do what it was doing before. If mass is moving at a constant speed, it wants to keep doing that. If it's sitting stock still, it would rather just sit there and not move. This is sort of obvious to us now, but think about the situation in 1650. It was obvious to the most casual observer that the standard state of matter is to be at rest. If you hit a cue ball, it rolls around the pool table for a while and then comes to a stop. Or even today, if you take your foot off the gas, the car slows down and stops, either because it runs into a tree or because it runs out of gas. The natural state of matter is to be at rest. That's common sense. It's obviously true, and by common sense, but it's wrong. And of course, this was Newton's genius really showing through. He understood that there were frictional forces at work that were causing the state of motion to change. The second law is, of course, what we torture introductory students with, namely F equals ma. That's, of course, basically a definition of force. If I have a mass, some number of atoms or some weight, and it accelerates, that means I'm applying a force, and I can define the force in that way. The third law says that if I have 2 bodies that are interacting by electromagnetic or gravitational means, that the force that one, let me try the pointer here, the force that one exerts on the other, F12, is equal to, in magnitude, the opposite force, F21, except they're pointed in opposite directions. So let's use, for example, the second law to calculate an interesting number. So if we consider a tackle, and let's keep it simple, we have 2 players, nominally 220 pounds each, so 100 kilograms. They're running at each other at top speed, nominally 10 yards, or we'll call yards equal to meters in this talk, 10 meters per second, and they collide. They end up lying on the ground. What's the force that one exerts on the other? And it's simply F equals ma. They exert the same amount of force on each other, but I now calculate this force by plugging in for the mass of the player, which is 100 kilograms. The acceleration is a little more tricky because I have to take the change, delta V, in the speed and divide by the time over which that hit occurs. So in the case of player A on the right, the change in speed is 10 meters per second. Before he was running flat out, and 0.15 seconds later, on average, he's lying on the ground, not moving. About 0.15 seconds is pretty typical for a collision in football, and gives us then, finally, when we plug everything in and multiply it, we get about 1,500 pounds, or 3/4 of a ton. The technical physics term for that is getting your bell rung. So these are big forces. My favorite, the best photo in all of football is this one. This is Chicago Bears number 51, who's exerting a large force on the entire Green Bay line and tackling him. May he rest in peace. That's Dick Butkus, the greatest linebacker that ever lived. So I talk to people about this. I give this talk to a lot of lay audiences, and they come up to me afterward and they say, well, you know, this is all well and good, but you're basically what you're saying is it's better to be a big, fast guy than a slow, small guy. Well, duh. I didn't need to go to physics class to learn that. And of course, they're right. It is better to be a big, fast guy than a slow, small guy. But there are some subtleties. And I'd like to show you one of these. Now, I understand I'm talking to an audience of professional physicists, so you may do better on this test than most groups do. But let's do the following thing. I have two blocks, two parallel pipe heads here, one made of wood, which weighs about 1.1 pounds. And then I have a sink brick of lead, roughly the same size, but it weighs 27 pounds. And now what I want to do is to support both of these on two styrofoam coffee cups. So I'll do that here. I put the brick on the cups, making sure that they're carefully aligned. This is a little tougher because if I don't do this carefully, the brick weighs so much that it will crush the coffee cups. So very gently, I set that down. And again, I'll align it like so. There we go. Now here's the question. I'm going to take a steel ball bearing, which weighs about 2 pounds, and I'm going to drop it from a fixed height. That's why we have this ruler here, to convince you that I'm not cheating. And the question is, which of these blocks will be more effective at crushing the coffee cup when I drop the ball from a fixed height? So who says the wood brick will be more effective? One person. No, 8. A third of you. Who says the lead brick will be more effective? Yeah, roughly the same number. Okay, it's a toss-up. I don't know. I'm not smart enough to figure it out. Let's do the experiment. So I'm going to take this again. I'm going to drop this from about 30 centimeters. I want to make sure it hits. Here we go. 3, 2, 1. And, you know, this cup is almost intact. This one got a little bit damaged. Now, let's use the lead brick. Here comes the exciting. I almost killed a regent doing this once. You know, tenure kills, professor kills regent, loses tenure. Yeah. Okay, so here we are, same height, 30 centimeters. 3, 2, 1. What? A little bit here. Nothing. I got nothing here. What's up with that? It's the first law. Mass wants to do what it was doing before. In this case, both masses were sitting stock still. the more mass you have, the more insistent it is on doing what it was doing before, which is not moving. So it doesn't crush the cups as effectively. When I give this talk, to the Lions Club or to Cub Scouts, you get about 98% of the audience saying, well, obviously, the lead brick will crush the cups more effectively. So they're somewhat taken aback when you do the experiment. Here's another example. I have a good demo here, but we don't have time for it. Here is Lawrence Taylor, maybe the second greatest rush end ever to play the game, cleaning out a Dallas quarterback. Taylor weighs roughly 260 pounds, and he's moving in at 10 meters per second, and he cleans out the quarterback. He sacks him badly. And the question is, okay, well, I've got a big, fast rush end, and I've got, the quarterback may weigh 190 pounds, soaking wet. Who exerts a bigger force on the other? Well, obviously, Taylor will exert a bigger force on the quarterback because he's the one that goes flying. And again, the answer is no. They both exert, by the third law, exactly the same force on the other. Now, you educated physicists know this, but I got into a long talk at one point with the senior science editor at the Boston Globe. Maybe it was Boston, maybe that was the problem. And he absolutely refused to believe this. He said, no, that can't be right. The other, that's a quarterback that goes flying, he's got to exert a smaller force. No, he's got less mass. That's why. And I gave up after literally an hour and a half. I couldn't convince him that this was the case. So if nothing else, we physics educators have a lot of work remaining to be done. So the thought I'd like to leave you with there is that Isaac Newton, who is certainly the greatest genius that ever lived, once said, I'm able to come up with these amazing physics laws because I stand on giants. And I actually managed to get a picture of that. There he is. See, New York, Meadowlands. Yeah, okay, never mind. I cracked myself up. So moving right along, let's talk a little bit about energy in a typical football play. So what I've plotted here is the average weight of NFL linemen over the years from 1920 to about 2010 when I made this slide about 2012 or something, and that's where I had data. So they can do that. The data is readily available from the Football Hall of Fame in Canton, Ohio. And you see that the mass has shifted from about 190 pounds back in 1920 when the Chicago Bears were the Decatur Staleys and we had the Massillon Tigers, up to about something a bit over 290 pounds. I'm sure it's up above 300 at this point. So the mass has grown by about 60%, 50 to 60% for linemen in the NFL. So the next question is, have they gotten faster? And the answer is almost certainly yes. They're in better shape than they ever were. They've got good nutrition. Now, the problem is they don't measure or don't store, don't archive 40 times for linemen. So the best thing we have is the world record speed in the 100-meter dash, which is readily available and starts out here. This is in feet per second because my editor made me do this. But starting out at nominally 30 feet per second and then moving up to something like 34 feet per second. Now, this is world-class sprinters. Of course, linemen aren't as fast as world-class sprinters, but the idea is their percentage increase should be roughly the same. And the world-class sprinters have come up by about 9.4, 10%, something like that. It's kind of interesting. There's this rise, and then there's this sort of plateau, and then there's this dramatic increase here. This, of course, is Usain Bolt, who's the greatest sprinter that ever lived, and who's it goes from here to here. So that's worth noting. But the takeaway is that the speed of athletes has probably gone up by about 10% in this time. If I combine the speed increase with the mass increase, I get the, there we go. Why isn't that working? This ought to, yeah, there we go. I get an increase in the energy, which is the thing that causes injuries, by roughly 100%, 85%. So this is just 1/2 mv squared, and it's increased due to those two components of increase, mass and velocity, and you get over that same period about 85%. This is the energy for linemen. It's dumped into the pit, and it's what causes injuries. It's what causes ankles to twist, bones to break, heads to concuss, etc. So one natural question is, why aren't there more injuries? The rate of injury in the NFL hasn't changed a lot. So, you know, if that's the case, why don't things like this happen more often? And we addressed that in the following video. This is one of the actual pieces that would be up on the Jumbotrons in Memorial Stadium. I'm hoping this will go. There we go.
To a player's head over a larger area. A sharp, concentrated blow to the head and delivered by a large force cause serious injury. But it's not the force that matters so much here, it's the pressure. The formula for pressure is force divided by the area over which the force is applied. From this equation, we can see why a carpenter, using a relatively small force, can drive a nail into a board. The cross-sectional area of the nail is relatively small. A helmet distributes the force of the head over a large area, thus reducing the pressure that the player's head feels. In the same way, the principle of distribution of force allows me to lie down on this bed of nails without significant injury.
So there's a pedagogical alarm bell here, and that is I've gotten more response to this video than any other video we did. We've probably done 100 of them over the course of time. Got more response to this one than any other one. And the response wants something, almost invariably wants something like this. How were you able to trick the camera into making it look like you can lie down on this bed of nails when we know you can't really do that? And you have to say, you know, the best thing I've ever come up, no, physics is real. Believe in physics. So this is an important issue. So in the 1920s, when about 20 to 25 players a year were dying who were playing college football, there was a big problem with skull fractures. They die because they would hit each other, and the helmets that they wore back then were essentially leather skull caps. Now we've got a much better situation. We've got polycarbonate shells. This innovation came along in 1931, and the force of a blow to the head is distributed over the entire surface of the helmet, thereby lowering the pressure, as we discussed in the video. There's another important idea here, a second mechanism for protection of the head, and that is that the impulse conformation has changed. In other words, if I hit a guy with my helmet in the head, his head will recoil with some momentum transfer, meaning some fixed impulse. Now, for a given speed that my head comes in with and delivers to the other person's head, conservation of momentum demands a specific impulse. But I can do that the easy way or the hard way. If I have head-on-head hits, the impulse, which is the integral, I don't show this slide to the Cub Scouts, is the integral under this curve. So I now plot the force. This is two heads on each other with no helmet in between. And you see something like this. With the foam in the helmet, however, and this is a very controversial and, well, the idea is not controversial. The practice of installation of foam is has an interesting and bizarre history, I get something that looks like this. It's the same reason that if I take an egg and I drop it from a height of 2 meters onto a cement floor, it breaks, but if I wrap it in foam, it doesn't break. The impulse needed to bring the egg to a halt is the same in either case, but I distribute that force over a longer period. Again, the impulse, the area under these two curves has to be the same, but for a longer time associated with the compression of the foam, I have to have then a lower force to make the integral the same. So these two ideas are what there are now essentially no deaths in football due to skull fractures. Okay, so the equipment has gotten better. What I want to now focus on for the rest of the talk is another problem associated with the football in flight. So let me first show you another video. This we did in the first year.
Symmetry is an important principle in physics and in football too. Consider the football itself. It has a long axis of rotational symmetry about which it can most easily spin. We all know that a coin standing on its edge will fall over unless it's spinning. In the same way, the football must be spinning for it to be stable in flight. As Eric will demonstrate, a well-formed football rotates about its long axis of symmetry. Eric's hand puts spin on the ball to stabilize it in flight for maximum yardage. Unfortunately, understanding the theoretical principle of symmetry doesn't guarantee instant success as a quarterback. Hey, Doc, you got a chance to run with your arm, and I think you're better suited for the offensive line.
So we did this video when our team was actually good, as opposed to the way it is now. But that was the last Heisman Trophy winner at Nebraska, Eric Crouch, who I've kept up with. I actually tutored him in physics. He was a kinesiology major, and I tutored him when he was coming through. So let's now talk about the ball in flight. And the first thing we need to talk about is air drag on the football. So we have an equation for the force of drag. It's equal to 1/2 times the density of the air, rho, times the drag coefficient, C sub d, times the area that the ball presents as it's to the onrushing air as the ball moves through. So if it's moving with its axis vertical to the perpendicular to the direction of velocity, then there'll be a relatively large area. But if it's moving with the axis parallel to the velocity vector, then it will be relatively small, and then that turns out to be multiplied by the velocity of the ball squared. This C sub d is indeed the coefficient of drag developed by aerodynamic engineers. In physics, we call this a fudge factor, because it has implicit in it some velocity dependence, because it's not really v squared, it's really like, depending on the velocity of the ball, v to the 2.4 or v to the 1.6 or something like that. So there is, again, an implicit velocity here. But that's the idea. So again, for perpendicular axes and velocity, we get a relatively large area, whereas for alignment, we get a somewhat smaller area. CD could vary between 0.1 and 0.6. Typical speed of a kickoff is about 30 meters per second, and the density of air is roughly 1.3 kilograms per cubic meter. When I plug all that in to get the drag force, I get something that is between 1.4 and 14 newtons. That factor of 10 is just fortuitous. But here's the point. The ball itself weighs 4 newtons. So that means that the drag force can be significantly greater than the weight of the ball. So lots of interesting things can happen. That's evident from this graph here. If I have a plot of height versus range on a kickoff, I kick the ball at 45 degrees launch angle with a launch speed of 100 feet per second. If I were to do that in a vacuum, I'd get a range of nominally 105 yards, something like that. But if I put air back in the stadium, which is a good thing to do, I get something closer to 80 yards. And if you notice carefully, there are two lines here. This corresponds to kicking the ball at, say, the Yale Bowl, which is the shorter yellow line, versus kicking it in, I think it's Qualcomm Stadium now, whatever the stadium is in Denver, which is this magenta line. So you get about a 5-yard difference depending on your altitude. And one important other thing that we learned from this is that professional kickers lie, because I talked to many of them over the years, and they all say, oh yeah, when I play in Denver, that darn ball will go 20 yards further. That's wrong. It won't go 20 yards further. It will go 5 yards further. And of course, I've also learned that professional kickers are extremely reluctant to tell you anything real about what they do because they're worried that you'll steal their secrets. So if we now look at the maximum, oh, by the way, here is what I get if I throw the ball, same angle, same speed, and I get that same difference here as well. So let's now look at the average kickoff distance versus altitude above sea level. The two different colors are just two different years. But what we see is that as I move from Foxborough out to Denver, I see a noticeable increase. So we take this data and we say, aha, it is true that the ball will go further the higher up you are. There's a problem here, and that is our conclusion, while it's hinted at by these data, why isn't this working out? While it's hinted at by these data, is really, the point is made strongly by these data up here, which violates Richard Feynman, may his name be praised, his rule that if your whole effect depends on one data point, don't rely on it. So really what we need to do is to take this point away. Again, we have a hint of it, but I would be very careful about drawing too many conclusions. This is just a fit. These black lines are a fit to the data. So I talk about this a lot, and as I mentioned before, I give this talk a lot to, say, Cub Scouts and Girl Scouts, and you can't do a lot of fancy demonstrations when you're, going over to their meeting place. But here's a demonstration that I do to illustrate the effect of air drag. So I have some book we got out of the library, and we have 10 sheets of white copy paper. And so I asked them, I said, well, I want to do an experiment now. I'm going to drop these two. And let's see which hits the ground first. Which one is going to hit the ground first? Any ideas? Yeah, the heavy one. Okay, I don't know. I don't know. Let's try it. Here we go. Ah, you were right. The heavy one hits the ground first. Why is that? Well, and now I take my, I risk everything and actually show them this diagram. I say, well, they both had about the same amount of air drag, that's the force upward, the F sub D, but the heavy one has a bigger F sub G downward, and the net downward force is greater proportional to the mass, and therefore the book accelerates more rapidly. So what that says is, though, that if I were to take the air drag away, like they did on the moon when they had the hammer and the feather. Remember, Alan Shepard did that back in 1974. They drop at the same rate and they hit the ground at the same time. So what I'd like to do is to now pump the air out of the room. Stephen said he had a big pump in the back somewhere. No, what I'd like to do is eliminate the air drag in the following way. I'm going to simply put the paper on top of the book. And now they hit at the same time. Now, I do this for the Girl Scouts, and most of them are kind of looking off and not paying attention. A few were paying attention. Maybe 1 out of 100 gets what I was saying, but that's not the goal. The goal is I want 10 or 15 out of 100 to go home and lose a full night's sleep worrying about this. If I can do that, I've succeeded in teaching them something. Okay, now let's move on to the following problem. Let's see, there we go. I gave this talk at the National Institute of Standards and Technology in Gaithersburg. It was our Christmas lecture back in 2000. And basically the same lecture you're getting. And at the end of it, though, Bill Phillips, who had just won the Nobel Prize, was sitting in the front row, and he raises his hand. And I thought, oh gosh, I've been to enough DAMOP meetings to know that if Bill Phillips raises his hand after a person's talk, that person has really screwed something up. I thought, oh gosh, what have I done? And he says, this is all well and good, but I have a question. Why is it when a quarterback throws a tight spiral pass, it turns over? That is to say, the axis of the ball maintains tangency with the line of the trajectory. So Bill, I thought, boy, I want to show him how smart I am. So I looked at him carefully and paused and then said, I have no idea. And I didn't. And that got me started on this problem. Why does the ball do this? Let me show you this video, which illustrates it nicely. You've got to wade through a bit of introduction, but we'll get to the tight spiral in about 45 seconds. Oops, that's not right. How do I get this guy? Nope. Why can't I? No, I had this trouble share. This is not, there's no way to get this going, is there? No. Okay, well, it shows tight spiral passes, which are very impressive. Indeed, that is the iconic NFL Films piece where the ball, they have the music playing in the background and the ball comes in and it's turning over beautifully. And you look at that and you say, geez, it really looks like there's some sort of negative feedback mechanism making that thing stay aligned. What's going on there? So the history of this is, I finally got to this slide. So Bill Phillips raised this question. So we went back in the literature and found a lot of literature on the topic, but there was nothing that was both conclusive and comprehensive or comprehensible. There was a fair number of ideas in the literature that were wrong. The work of, I think it's his first name is Henry Sudak and Bill Ray did explain what's going on, but they did so. They weren't interested in the problem and they never comment on it, but buried in their math and some of their graphs shows that their calculations do in fact give that turnover, but it's nothing you could ever take away as a simple idea. So that's what we were interested in doing. I gave a talk about 3 months after I'd given it at NIST. I gave it at NASA Greenbelt. And I explained that there was this new problem I was worried about, which why does the ball turn over? And at the end of the talk, an old Nazi comes up to me and says, oh, we solved that problem at Peenemünde. Here's a picture of a Nazi and an A4 right here. And I said, wow, great. And he said, I will send you all of our stuff. Did not hear back from him. And about a year later, I just gave up and called. I didn't know who he was. I didn't know his name. I just knew that he claimed to have solved the problem when he was working on the A4. and I called Aaron Temkin and said, hey, whatever happened to that guy that worked for the Germans and had an A4 and solved my problem? He said, oh, yeah, he died the week after you gave the talk. So that didn't work. Tried some ideas. And then it turned out that I was sitting at the first APS research medal was given to Ed Whitten, and there was a big banquet at the Willard Hotel, and I was sitting at a table in the audience, and sitting next to me was Richard Price, who's a theorist at MIT. And, we're kind of waiting for things to kick off. And I said, what do you do? And he was explaining about GR and all this stuff. And he said, what do you do? And I said, well, I do neutrino physics and electron physics, but I'm also interested in football. And I explained the problem to him. And he says, this we've got to solve. So he got very interested. And so I called in. After 15 years, I just decided I'm not smart enough to solve this problem on my own. I'll get two really smart theorists to look into it for me. So I was joined in the effort by Willie Moss, who is a college buddy of mine, and Richard Price at MIT. So here's the basic issue. So if I, again, pump all the air out of the room, the ball will maintain its axis in the initial angle because of conservation of angular momentum. What a tight spiral pass does is to turn over, that is to say, its axis changes from here to here. In that time, the spin drag of the air, in other words, the air trying to slow the spin down, is negligible. It approximately maintains its same angular momentum about its axis. So what's hard to get your mind around is that it starts out with this L and it finishes with this L. And so that means the change in L, or proportional to the torque that I apply, has to be vertically downward. The problem with that is that corresponds to some force trying to cause the ball to rotate in a horizontal plane. And that's not what's going on. There's no force to the side. So what's happening? So we start to think a bit harder, and we say, maybe it's like a weather vane. Maybe it's turning over because that it just like a weather vane lines up. The problem with that is that the weather vane has a dipole moment, a mass dipole, whereas a football doesn't. So the reason a weather vane lines up is because the wind pushes harder here than it does here. That's not available with a football. So that turns out to be wrong. And then a number of papers have talked about, well, if I take a sleeping top, one that's spinning very rapidly and has got a vertical axis, if you perturb the axis with a brief impulse, it will return to vertical. That's why they call it a sleeping top, I guess. And it's because it's rolling around. Its axis the axis orientation is defined by some angle theta, and there's some Lagrangian minimum at the center of the theta map. So that's why this must be happening. But that's not what's going on with the football. With the football, what we have is a ball that is thrown this way, and over time, within the first half second of the flight, gravity has now brought the velocity down from this original orientation, simply because the ball is describing a parabolic path. Now what I have is a torque, which is trying to make this ball tumble end over end. And so the torque now is pointing to the left, to the ball's right, and not vertically downward. So how can that be? It turns out we looked into this issue as well. So here's what I have. What is a tight spiral pass? It's a pass in which the velocity and the angular momentum and the axis of the ball here, an S unit vector, are all aligned perfectly. And now what I get as the line of trajectory begins to fall off its original orientation is a force providing a torque that is horizontal. And it turns out Bill Ray did some very nice experiments with a spinning football at 600 RPM, which is about what a tight spiral is, that plots this torque as a function of its pitch angle. And that turns out, as you would expect, to be proportional to sine 2 theta, to good accuracy. When theta is 0, the torque has to be 0 by symmetry. When the angle is 90 degrees, the torque has to be 0 by symmetry. So you get a sine 2 theta effect. There's another interesting thing going on. This is something close to I worry a lot about chirality. Bart Starr, in his 1967 book on quarterbacking, notes that if he throws a ball a long distance, it veers to the right. Whereas if it's thrown by Warren Moon, who's left-handed, the ball veers to the left. So what's up with that? It turns out that's a bit easier to understand. We'll get there in a second. So we worked out what this really was. The real problem here was that I did not understand chapter 8 in Goldstein. If you understand rigid body motion, this problem becomes a lot easier conceptually, but I mean really understand. And you know, in grad school, in college and grad school, we skipped over that chapter quickly. So these are the torque equations. I won't go into them in detail. There's a nice equation here, which isn't in any book we could find, but Harry Sudak came up with it. We're going to launch the ball at 30 degrees. It's going to have a speed of nominally 30 meters per second. And we're going to assume that its range of flight is that given, assuming there's no air drag. That is to say, we're only going to use the air drag to worry about the torque on the ball, not the force itself. So we assume a parabolic flight in a vertical plane. When we do that, what we find is this. If I now plot the angle that the ball's axis makes with the line of velocity, we find that it makes this nice circle, which has a radius of nominally 0.15 radians, or what is that? That's roughly 7 degrees, 7 or 8 degrees. And it's precessing around a point here, which turns out to correspond to a veer to the right. In other words, what's happening is, and I'll do this right now, and I'll come back to another point. Well, there's an interesting idea. I'll just say this quickly. If you notice carefully, you notice this is not a perfect circle. It's got a mild crenellation to it. And we didn't understand that for a long time, and we assumed it was some problem with our computer code or something. If I throw the ball with an initial pitch up, i.e. not a perfect pass, not a perfect spiral pass, I get essentially the same behavior, but with a more noticeable precession or a more noticeable nutation. And that is a very important idea. I'll just leave this for the theorists. In the literature up to this point, people had said, oh, that wobble, if you don't throw it perfectly, that's torque-free precession. We said, oh yeah, that's obvious. And several people they'd done video captures of balls flying through the air, said, look, given our numbers, that corresponds exactly to the frequency of torque-free precession. But I mean, you think about it for a second, there's no torque-free precession going on here. There's lots of torque. So what do we have? What we have is nutation. And nutation happens under torque. And the thing that really made me upset with God about this is that the wobble frequency due to torque-free precession is in fact exactly the same as the frequency of nutation. So the two have the same value. So yes, of course, we were seeing that frequency, but it's not due to torque-free precession, it's due to nutation. So that turned out to be a major help, in a breakthrough in the understanding. So very simply this. When the ball is essentially pitched up because the line of trajectory is falling below it, there is a pitch torque which points along Y. The ball is moving initially along Z, and that tries to make the ball that applies a torque here. But remember that L is along the axis of the ball. So any change due to this torque will indeed be horizontal as before. So what we essentially have now is a ball that has yawed to the right as the quarterback sees it. And now, of course, there's also a yaw torque, which is trying to make the ball go down. In other words, this is really simply precession. It's harmonic precession, and that's exactly what's going on. The important point about Bart Starr's conundrum is that as soon as the ball rotates over, I now have net force, not just torque, but net force pushing the ball to the quarterback's right, which is why the ball veers. So we then plugged all this in. We made a very simplifying assumption about the arc, saying that it's not a parabola, it's a circle. And when you do that, you can come up with an analytic solution to second order. And what we see then is that the numerical solution and the analytic solution are right on top of each other. So here's the explanation to Bill Phillips' question. Why does the ball turn over? If I take a top and start it with an angle relative to the vertical, it will precess, but its average orientation will be vertical. The ball wants to precess around the force line. Exactly the same thing happens in this case, except we replace the force of gravity with the force of the air drag. So now that force, which starts out, remember, opposite the velocity, is always pointing opposite the velocity. So the ball thinks of that as its new vertical. So it rotates about that ever-changing point and maintains what looks like a fairly close alignment. It's not perfect. It is precessing around that point. But since there's only about, let me go back a second, since there are only there's about one full cycle of precession for the entire arc of the pass, it just basically looks like it's locked on to this point. Keep in mind also that, oh, I'm pointing that doesn't help. This point here is the actual final orientation. We don't have that in our model, but this is really just rotating about the orientation of the ball. And the average is off to the right because the quarterback was right-handed. And I'll leave it at that. Just one other quick fun story I'll share with you. There's a lot of confusion in the sports reporting about football. I like this one especially because it got resolved in the magazine Sports Illustrated. So hang time is good on a punt because you would like your players to get down there at the end of the field and down the ball at the 1-inch line to give your defense an advantage after a punt. So hang time is good. Let's fill the ball with helium. After all, I mean, the Goodyear blimp has great hang time. So Sports Illustrated decided to do this, and they had some poor kicker kick the ball filled with helium. They filled up footballs with the same pressure of helium and air, and had a kicker kick 20 kicks with helium and 20 kicks with air. And what they discovered was that indeed the helium ball does go further, presumably because of that enhanced hang time, except when you look at the data, this is what you find. This is basically what the data was. And if you see, clearly the helium ball goes further than the air-filled ball. But of course, if you consider, the editors of Sports Illustrated do not understand the concept of uncertainty or standard deviations. In fact, if you think about it, the helium ball should go not as far because it's more like a wiffle ball, which goes further with a given velocity and angle. Well, a baseball or a wiffle ball? The answer is a baseball will go further because even though the air drag force is the same, the mass keeps it going at more with less loss. So I think with that, I'd like to stop. I have a couple of people that it's important to thank. I mentioned Richard Price, who is still up at MIT, although I think he just retired last year. And he's been there for quite some time. Willie Moss was my best friend at Caltech, and has been at Livermore forever. The person I'd really like to thank, though, is Bob Adair. When I was writing my book, my editor calls me up and says, you know, we in the popular reading industry don't believe in fact checking anymore. So because I'd asked, you know, when are we bringing the fact checker in to go through this stuff? He said, we don't have those. We don't pay for those anymore. They're not in budget. I thought, oh, crap. So I had been a great admirer of Bob's book that Steve mentioned for years. And I knew him from my Yale days. So I called him up and said, would you be willing to take a look at my manuscript? He said, sure. Generously said, yeah, sure, I'll take a look at it. I sent it off to him. He returned it 2 weeks later with 7 pages of detailed notes, all of which were incredibly helpful. So Bob Adair was my fact checker, and my hope is that with his help, I was able to produce something that was certainly not as good as his book, but in maybe the same ballpark. And here's the book, and you can buy it for the low, low price of $11.95 from Amazon. They make great stocking stuffers, and I'll leave it at that. Thank you very much.
We have time for a few questions, if anybody.
I'm loud enough. Can you comment on the deflate gate?
Yes, I can. In a nutshell, the Patriots cheated. That was an interesting. So this whole deflate gate thing came down, and the first people they asked were Bill Nye, the science guy.
I don't think you can assume everybody here knows what.
Oh, sorry. Let me hold on. We may get lucky here. Yes, addendum, deflate gate. So in the 2015 AFC Championship, the Pats edged the Colts 45-7. At halftime, the Patriots have a lower pressure than their initially determined value by about 1.3 PSIG. The cognoscenti are consulted, that being Neil deGrasse Tyson and Bill Nye, the science guy, who did not know the difference between PSI and PSIG. And it turned out if you worked with PSI, if you worked with the actual pressures that were reported, it didn't seem like there could be any problem. But as soon as you correct for PSIG, then there is a problem. It's important to note that the scientist in that group, Neil deGrasse Tyson, immediately, I think I called him up and yelled at him, but immediately acknowledged his error and put it in print and said, oh, I screwed this up and here's why, and et cetera, et cetera. Bill Nye, the science guy, did nothing. And then this slide was on my concussion talk, and I worried that maybe they were trying to divert attention from the concussion problem they have. So the bottom line is, this kept going on for a while, and I was, with my fully functioning ego, getting angrier and angrier that they weren't calling on me. After all, darn it, I wrote the book. They should be calling me. So the report so they finally farmed the problem out to an engineering group at Princeton who wrote a beautiful report, which was exactly correct. And they point out the fact that you've got thermal lag, and they pointed out all the right things and isochoric processes, and et cetera, and showed very convincingly that the Patriots had indeed cheated. It's not clear they got any advantage from it, but they had cheated.
Meaning that there was no physical explanation in terms of temperature or anything.
That's correct. Yeah, they eliminated all of the possibilities. So the report came out, and I get this call from the it was the Los Angeles Times. The Los Angeles Times called me up and said, what do you think about that report? I said, well, it's about time. You should have called me 4 months ago. I could have explained all this to you. He said, no, we would never have called you. I said, Why not? Because you're a tainted witness. Bill Belichick wrote the foreword to my book. So I was I'm contractually obligated to root for the Patriots, I guess. So the Patriots cheated, and that's the bottom line. I could give you another talk about that. I've got lots and lots of slides. Yes, sir.
So I guess one of the interesting implications of your simulation and model for the flight is that no matter how well you do, it's gonna wobble a little bit.
Yes,
And that's why when they slow it down
yes,
with the super slow mo,
right.
you know, it can never be exactly.
There is no such thing as a perfect pass with no nutation. But that very slight wobbling that you see, that really had us going for, I thought, okay, here I'm a dumb experimentalist. I brought in these two brilliant theorists to solve the problem, and we still spent the next 3 years yelling at each other over Zoom. There were just a lot of subtleties to the problem. And one of the breakthroughs really was when we realized two things. One is, we'll get there eventually, that this effect right here is real and it's nutation. And then with my newfound understanding of Goldstein, chapter 8, it turns out, and you have to really, it's not in the first edition, which is what I had. It's in the third edition. These two are in fact exactly the same. There is no torque-free precession. There is only nutation. Yeah. Yes.
So you showed a slide that had a rocket or something. And
Yes.
concept actually being used.
Well, I think so. Of course, the reason, all I know is that this guy who died claimed that he knew what the problem was. What I do, and so he said, I used to work at Pinamunda. Okay, so for visual excitement, I just the reason, of course, that they put fins on the A4 and indeed on any rocket before inertial guidance is to keep it from rotating. They don't want it to rotate. Now that's weird because you would like it to turn over, given that the warhead we should be pointing down when it hits London. What's the Tom Lear thing? That's not my problem, says Werner von Braun. Yeah. But okay. Well, another quick story about that. So I went after I talked to him before he died, presumably. I went to the library, and it turns out that when the English or the Americans, I forget, liberated Peenemünde, they turned it back over to the Dutch, and the Dutch got all of the scientific records from Peenemünde and translated them into English. Thank you. And they do talk about the effect that artillery shells will spin and turn over, but that mathematical discussion, they say in these notes from Peenemünde, is too difficult to discuss in detail, and we'll leave it to somebody else to solve, I guess. So there is an intimation that they were aware of the problem, but there's no real solution. I want to emphasize that the work by Sudak and Ray in effect solved the problem. It's just that they didn't concentrate on it. And they're both papers are full of what, at least for me, was incomprehensible, overly detailed engineering tainted mathematics. They got 2 pages of glossary of different symbols. So you've got to get familiar with 48 different symbols as you're reading through this. It's all there. Ray does a calculation, and indeed it does show the turnover, but he never comments on it. Yes.
Knowing this, suppose you had to design a football for an indoor game. But what would you change, the standard NFL football?
I don't know. I think it's pretty optimal. Maybe because you can throw this thing keep it, okay, so as we all know or should know, the game of American football was invented by Yale and Harvard together. First real American football game was the second Yale-Harvard game. And Walter Camp of Yale University changed the rugby ball so that it would be easier to throw. So that question would have great significance if asked in 1920, because that's when they were dealing, in 1910, they were basically still playing American football with a rugby ball, and passing was rarely done. So I can't think, so there was one coach at Nebraska that was actually interested in physics of football, and invited me over periodically. He was summarily fired after that, but and he received once a week in the mail footballs from various manufacturers that were trying to improve things. And there's a fair range in terms of weight and aspect ratio for the ball that the rules allow. And we could never see any obvious improvement. We had the quarterbacks go out there and throw them, and they said, it's all about the same. Keep in mind that the quarterbacks don't know any of this stuff, but how do you make a ball that's wobbling a little bit and veering quite noticeably to the right if you're right-handed? How do you make that ball catch up to your receiver who's 50 yards downfield? The answer has nothing to do with physics. It's practice, practice, practice. So they have a gut feeling for what's going to happen with the ball. Yes, sir.
A lot of interest in the whole analytics thing in this day and age. Have you ever looked into or been asked to look into anything predictive or?
Well, I haven't done this, but we've talked about it a lot. And that is, it would be interesting. In fact, Bill Ray does it a little bit. He says, what should the attitude of the ball be in order to make it go as far as possible? And he does consider that problem. So there is a prediction that would be of obvious utility to a quarterback, except that it results in changes. Yep, it'll go 5 inches further if you align that ball to within 0.21 degrees of where you normally throw it. You'll get another 5 inches of distance. So that we've thought about that, hoping to get rich, but it hasn't occurred yet. But that's a good idea. Yes, ma'am.
The way that the ball is from, in fact, the most like spin pattern.
Well, you want a tight spiral pass because it'll go furthest. The way you have to do that is to get it spinning as rapidly as possible. And so what the great quarterbacks do, like Patrick Mahomes, is to roll it off their fingers for as long as possible and to push it. The impulse needs to be as big as possible to get the ball moving as rapidly as possible. There are tricks that you read about, on the internet about how to flick your wrist or something at the end. But really, I would say that the best thing is to make sure that you can see that the spin and the velocity and the angular momentum are aligned perfectly. If the angular momentum is off, it will do something akin to torque-free precession, because now L is pointing off in some weird direction, even though S is down this way. So yeah, I would love to be able to put specific. Here's a very interesting thing, though, and that is so maybe the most interesting thing in the book, because the book was written before I understood the tight spiral pass, is, and I got this from a coach for the New England Patriots, is if you have a punt, sometimes the punt turns over. So I'm punting the ball from here to here. And sometimes the punt turns over just like a tight spiral pass. Sometimes, for reasons which I don't understand, the punt doesn't turn over. So it maintains this axis. It's spinning along this axis. And now what happens is, if you think of it as a tight spiral pass so that it turns over, it's going to veer to the right, just like Bart Starr says it should. If it doesn't turn over and it's coming down this way, now its spin is perpendicular to its velocity, and that's the Magnus force. That's curveball. Bend it like Beckham. The ball will veer the other way. So what my friend said is, what I teach my punt returners is, if the ball turns over, go this way. If the punt doesn't turn over, go the other way. And that's a totally physics, and he didn't know why that was, and I explained it to him and put it in the book because it's a neat little, that's the one thing in the darn book that coaches generally don't know. Yeah.
Fantastic talk. Do you have in 2 minutes,
Yeah.
comment on concussions? Any ideas about how to reduce them?
Yeah. So concussions are a real problem. They're probably a bigger problem for linemen than they are for the skill players. I take offense at that being an ex-lineman, for the skill players. Because the skill players, you know, the cornerbacks will get a big hit once every 10 plays or something, but the linemen, every play, it's just bang, bang. And I think that really causes a lot of problems with CTE. Indeed, for the few linemen that have had their heads cut open after they died, it's at least as bad as it is for the guys running, the running backs and the corners. I think we're not going to be able to do a lot better. Football is an inherently violent game. Polycarbonate shells really solved 98% of them. I mean, the deaths have dropped to 0. There are some issues related to foam that can make things better, but only 10% better. I mean, if you're talking about maximum force, foam will help you a little bit. And there's a lot of discussion about how to, I don't think I have it here. Maybe I have it. Maybe we'll get lucky. There's a really cool diagram. Boy. Yeah, oh, here it is. Great. So this is foam, and foam can be stiff or foam can be soft. If foam is really, really stiff, where'd the pointer go? If foam is really stiff, what you get is something like this. And this is it's very stiff. So, you know, in a Hooke's law force versus compression diagram, it comes up rapidly and you have a large force. If it's too soft, it bottoms out and then you get a really large force. So there's some foam right in the middle. That's why we call this the Goldilocks diagram. It's just right in here someplace. And the goal is to, you know, use that kind of foam. There's huge effects due to temperature dependence. Bottom line, to answer your question, I think we can make the incidence of serious concussions maybe 10% better, but no more. Final point. It turns out if you put 100 doctors in a room and say, what is a concussion? You'll get 100 different answers. Then you say, all right, well, in the interests of unanimity, how do I prevent a concussion? And you'll get another 100 different answers. One thing that's slowly emerging in the epidemiology is that a torque is worse than a direct hit. So if your brain rotates in its brain case, that's probably worse. The limited evidence seems to point to the idea that that's probably going to be more prone to causing a concussion than a direct force. So torque bad in this case. And thank you guys for inventing football, or at least thank Walter Camp for inventing football.
Okay. Thank you. If there's no more questions, I guess this is it. And thank you very much.
Thank you very much. It's an honor to give the physics club talk.